All right, section 8.4, hypothesis test for one standard deviation. What's our notation for a population standard deviation? What's that symbol look like? Sigma. So when you're writing your claims, when you're writing your hypothesis test, your HO and your HA, they should always have either a mu, a sigma, or a p. Later on, we're going to expand that a little bit, but that should be most of what we're going to work with. Now, kind of like our work with confidence intervals for a population standard deviation, there's a requirement here for hypothesis tests that we just can't get around. And that is your data must come from a normal distribution. Your data comes from a normal distribution. So that's our assumption. How can you check that? We just went over those things in section 8.2. How can you check that your data actually comes from a normal distribution? Ooh, nice, nice. So, histogram, Ryan Joyner test, no more than one. Yeah, QQ plot or a normal quantile plot. Those are synonyms. Ryan Joyner test if you want to really be fancy, but you know, look, if you get 2 or 3 of these, I'll be pretty happy. If you get 4, I'll be ecstatic. In any case, there's a lot of different ways we can look and decide if we have normally distributed data. In the case of hypothesis tests, Madison, in the case of hypothesis tests for population standard deviation, it's really vital and important that you actually have normally distributed data. This is a horrible test to do without that assumption. In fact, if your data isn't normally distributed, just don't use this test. There's other things we can do. Now, this first one has got a lot going on it. So let me help you try and unpack it. What's happening is you're going to have somebody who's manufacturing hand pumps with a 0.7-inch diameter, and they change their process a little bit. They recalibrate things, and they want to see, has it gotten any better? Do you have more consistency? Now, more consistency would mean what? Is your standard deviation increasing or decreasing if you're trying to be more consistent? Decreasing. So that's what we're going to see in this problem. Now, let's see. The manager determines that diameters are normally distributed, so that's something that we need, normally distributed, with a mean of 0.7 inch and a standard deviation of 0.003 inches. So that's pretty small. After recalibrating the projection machine, the manager randomly selects 23 pistons and determines that the standard deviation is 0.0022. Now, there's a couple things here that I want to highlight. We got 23 pistons, and they have a standard deviation of 0.0022. This is your sample. This is your sample data, so that's going to be S right there. It's not sigma. What about the 23 here? Well, that's going to be your N. So those are a couple of statistics that we're going to use to conduct a hypothesis test. The hypothesis test that we're going to conduct is to see if the standard deviation has changed. And in fact, we want to see if the standard deviation has decreased. So these two things in yellow are going together. This was the standard deviation. That's what we're accepting. We want to see, has that gotten better after you recalibrate it? And we're going to do that with our sample here. The question that you're going to have to face first off is, what's the original claim? What should I draw there? What should I write there? Well, let's start with the parameter. What parameter am I testing here? Sigma, right? Because you're talking about a claim regarding standard deviation, so it's going to be sigma. Okay. And what do we want to see? We want to see if that standard deviation has decreased. Well, that would be decreased from the original standard deviation before they calibrated the machine. Go ahead, say it again. Less than, thank you. So less than 0.003. So that's your original claim. It's important that you be able to parse through these things and figure that out. Now once you figure that out, set up your HO and HA, your null and alternative hypothesis. And what's up, Oz?
You lost me there.
What? To take this and then use it to set up these two?
Sure.
Okay. Are you okay with what we got here in yellow?
Yeah.
All right, because we're looking to see if the standard deviation has decreased from what it was.
But why is it that standard deviation and not the other standard deviation as the
This-
regular claim?
This is our sample data, and we're going to use our sample data to test if it's changed from the original population standard deviation. So this was the accepted value for the standard deviation. It's been 0.03 for a long time. We make some changes, and then we collected some data and said, all right, has it changed from its original standard deviation? Has it decreased?
Okay.
So is this going to be part of HO or HA?
HA.
HA. Sigma is less than 0.003. What am I going to put here? Greater than or equal to. Now, just a reminder, when you're doing this in my stat lab, they're not going to give you the less than or equal to or greater than or equal to option. What are they going to write there instead? Equal. And that's for my stat lab. Yeah, I mean, I don't know. I think it's just a little easier for you to think about it this way, but, you know, obviously they don't exactly agree with me. Let me transfer that over to here. So we got HO, sigma is greater than or equal to 0.003, and then HA, sigma is less than 0.003. We're going to test this at the alpha equals 10% level. That's pretty high. It's really only when you're doing, book work like this that you're going to use alpha of 0.1 or something like that. The typical values that you're going to use are 0.05 and 0.01. Those are the typical values that you use. Okay, so let's keep going then. We're going to do a hypothesis test. Let's input the data. Analysis, hypothesis testing. Which one am I going to choose this time?
Oh, wait. Never mind.
Standard deviation, one sample. Looking good there. We want to use summary statistics. Angie, help me out. Which one of these should I use as an alternative hypothesis? The first one, second one, or third one?
The third one.
Good. Third one? All right, so let's click that. Our significance level is a rather large 0.10. Thanks, Angie. And Liv, what's the claimed standard deviation in this particular problem? Yes.
The 0.003.
Yeah. So that's our claim standard deviation. You're always going to find that number in your null hypothesis. So 0.003. Our sample size was 23. And our sample standard deviation, well, we did write that down, or take note of it. That was 0.0022. 0.0022. And bam. What do I need from this problem or the output here at this point? What am I looking for? P-value. Good. So we got a p-value of 0.0392. We'll call it 0.0392. So we got step 1 here, step 2, step 3. We input the data. Step 4, p-value is 0.0392. That brings us to step 5. Is our p-value less than alpha? Yep. P is less than alpha. This is less than 0.10, so therefore we reject H naught. Let's look back now and try and figure out how we're going to word our conclusion. This is your original claim. Sigma is less than 0.003. Work it through. See if you can't figure out which one of these we're going to use. Oh, that's the claimed. This is the claimed value of sigma. It's not the original claim. It's just the claimed value. That's what you have to use for your hypothesis test. So it's just asking for that number. It's not the same as the original claim.
So when we're doing 5, we're looking at it.
Yeah.
P and alpha.
All right, let's take a look at these. Derek, does our original claim contain the condition of equality? No, so we're branched down. Do we reject H naught? So that brings us to C. The sample data support the claim that. All right. Sample data support the claim that the standard deviation of, what was those things, the pumps, of hand pump diameters has decreased. Whew. All right. Lot going on with that one.
Good job.
Good job. There's one more I'd like to do like this. I hope you're seeing that we're doing the same kind of thing again and again with these hypothesis test. I've structured it that way so that way you get comfortable and familiar. It's always going to be state your null and alternative hypothesis, decide on alpha, input your data, find your p-value, reject H0 or fail to reject H0, and then state your conclusion in words. Now we can do that for a lot of different circumstances, but that's going to be the general flow in all of these. So, is there any comment on this first one for section 8.4? I want to do one more, and then I want to give you a chance to work on some yourself. Yes, Marvin.
So for the last part, for I guess step 7, the 80% confidence interval, we said it was less than 0.003, and if it's true, then that kind of helps us check ourselves that
So,
we did it right.
one thing here, our value of alpha was 10%, right? So we should have a 90% confidence interval if we want to check this and we want to be fair about it. So if you wanted to check it and be fair about it, then there's a couple ways you can do it, but I think what I would recommend is that we go back to analysis and then go to confidence intervals, standard deviation 1 sample, and set up the confidence interval that we actually want, which would be 0, which would be a 90% confidence interval. Sample size was 23. Sample standard deviation was 0.0022. And then now this is your confidence interval. And we can feel good about our conclusion because this confidence interval does not contain 0.003. We rejected the idea that it would contain 0.003. Since our confidence interval doesn't, then this confidence interval matches our conclusion from the hypothesis test.
So it tells us we did it right.
Yeah, it's a nice confirmation. It's a nice way to double check your work on this one. So appreciate the question on that. Thank you. Let's move down to example B. And take a look what we got going here. Now example B talks about something that we haven't looked at in a while. It's kind of like your range rule of thumb. So let me try and remind you of what's going on there. So range rule of thumb. And that pertained to basically the empirical rule. So let's take a look at a normal distribution. That's the mean. And I can move out one standard deviation away from the mean. How much of the data is going to be between those 2 points on a normal curve? You remember those numbers?
68%.
Yeah, about 68% is going to be between here and here. I can go a little further, maybe move 2 standard deviations away from the mean. So mu plus 2 sigma and mu minus 2 sigma. How much of the data is now between these two? 95% of your data. So almost all of your data is going to be within those 2 standard deviations. Now let's count how many standard deviations separate the top from the bottom. I've got 1 here, 1 here, 1 here, and 1 here. How many standard deviations separate those 2? 4 standard deviations. So the range of your data, you remember the range? Range of your data was the top minus the bottom, is going to be approximately 4 times the standard deviation. If you wanted to actually find an approximation for the standard deviation, how could you solve this for sigma? What would you do? Well, treat this as an inequality, or an equality. Range equals 4 sigma. How would you solve for sigma in something like this? What's the opposite of multiplying by 4? Divide by 4. So you get the range divided by 4 equals sigma. And let's put this in approximately. It's a good way to try and estimate the standard deviation kind of in a quick and dirty fashion. It's not perfect, but they actually use it in this particular problem. So that's why I mentioned it here. So let's see how they're using it. Simple random sample of 35 men from a normally distributed population. So once again, they're giving you that little bit of information that we need. Results in a standard deviation of 12.2 beats per minute. What symbol should I use for that 12.2 beats per minute? Is this sample data or is that population data? Yes, so it's sample data, so S. The normal range of pulse rates for adults is typically given to be 60 to 100 beats. So 60 to 100, if that's the normal range, or the normal gap between top and bottom, what's the range here? Yeah, 100 minus 60 equals 40. If I divide that by 4, what do I get for an estimate for sigma? 10. So that's exactly what they're doing in this problem. They're saying, okay, if we apply the range rule of thumb, then we get a standard deviation of 10 beats per minute. So that's going to be our sigma in this particular problem. Sigma is 10. Oops, wrong way. Use the sample results with a 10% significance level to test the claim that the pulse rates of men have a standard deviation equal to 10 beats per minute. So right here, they're giving you your original claim. It says it right here. Test the claim that pulse rates of men have a standard deviation equal to 10 beats per minute. So let's write that in terms of symbols. In terms of symbols, Amy, what would that be?
I'm sorry, can you repeat that?
In terms of symbols, what would that be? What's the original claim in terms of symbols?
That the standard deviation equals 10.
Yeah. So what symbol do I use for standard deviation?
Sigma.
Yeah, sigma. Good. So sigma equals 10. Angie, is this going to be part of my null or alternative hypothesis?
No.
All right, the null hypothesis. Garrett, if that's part of my null hypothesis, what should be my alternative hypothesis? Not equal to. Thank you. Now they already told us what alpha is. Alpha is 0.10. So we're looking okay there. Next step was we need to do what? What do we need to do next?
Input data.
Input the data. Yeah. So we're going to have to input some numbers here. Those numbers are going to include the 12.2 standard deviation, or 12.2 beats per minute for S. And then we had a value for N too, right? 35 men. So these two numbers right here. All right. So we want those two. Let's go back to stat disk. Analysis, hypothesis testing, standard deviation. Madison, is there something I can help out with? No? Okay. Which one of these should I use here? First one, second one, or third one for the alternative? Somebody said none. All right, first one. Significance level is 0.10. Claimed standard deviation. So, Nick, claimed standard deviation and original claim are different things. So the claimed standard deviation, that claimed number, is going to come from our null hypothesis. But it's not exactly directly related to the original claim. Our original claim was this part right here. That's the original claim. Original claim. But the claimed standard deviation, that number you're just going to look for right here. All right? So maybe there is some little relationship here, but in my mind they're referring to a little bit different things. So let's go put in the claimed standard deviation. Well, that was 10. Sample size was what, 35? We had 35. Yep, 35 men. So let's put in 35. Sample standard deviation was 12 something, right? 12.2. Now there is one nice thing that they gave us that allowed us to do this problem. Does anyone know what that is? They gave us that it was normally distributed. All right, so that's a must. You can test those things as needed and as discussed before. Let's actually evaluate this. What do I need from this page here right now? What am I looking for? What do I need? The p-value. Thank you. So the p-value in this case is 0.066. That brings us to step 5. You want to try that one, Liv?
I just had a question.
Sure.
Do we just stop the question if it's not normally distributed? Just don't do it?
Say again?
If it's not normally distributed?
Yeah, if it's not normally distributed, you would just stop. You just grind to a halt. Now, there are other ways you can do these types of problems when when you don't have a normal distribution. One of them is a method we didn't cover in section 7.4, and that would be bootstrapping. But that's beyond what we've covered, so I'm not going to hold you responsible for that kind of thing.
Can you remind me how we figured out if it was normally distributed for egg?
Both of these said that it was normally distributed. Yeah, normally distributed right there, and normally distributed here. Yeah. No, I appreciate you asking. What are we going to do with our null hypothesis? Do we fail reject or do we reject H naught? Reject. What if I change my value of alpha to 0.05? Would that change my conclusion here?
No.
Wait.
Yeah, you would fail to reject.
Yeah, if alpha was 0.05, you would fail to reject. So the nice thing about reporting your p-value is that people can make their own decisions. Somebody might say, yeah, I'd reject. Somebody else might say, no, that's too big. Your p-value is basically the probability that H naught could be true for your given data set. So if this is really small, you don't think that there's going to be a good chance that H naught can be true, so you'll reject it. If this is larger, you might start thinking, well, I don't think I trust that. Or I don't want to reject it, so you won't. In this case, we're going to reject H naught.
I was going to say, are we going to get any where we fail to reject?
It's more fun to reject, although that actually is, it is a problem in industry. In particular, Oz, no, this is a serious question. I mean, do you get some that you fail to reject? Absolutely. It's a problem in the pharmaceutical industry because they need significant results. And a lot of times they don't publish their results if they don't find a significant test, or that they show that their drug is better than something else. So they get shelved. But that data could help somebody else out, and it's become a real problem. You can read a book called Bad Pharma if you want to find out more about that kind of stuff. All right, last but not least, number 6. Let's see about which claim we're going to use here, or which form of our hypothesis test. Here's your original claim. It contains a possibility of equality. Do you reject? Yes. So there's sufficient evidence to warrant rejection of the claim that standard deviation of pulse rates of men is equal to 10 beats per minute.
That's me.
There is sufficient evidence to warrant rejection of the claim if I want a confidence interval as part of this, I'll ask for it. The problem is when I start piling on hypothesis tests and then a confidence interval, it just starts to get long.
Yeah, do that.
So now it's not a bad idea to check that. I mean, Marvin was noting that earlier, is that it's usually a good double check of your work that your conclusion from the confidence interval matches your conclusion from the hypothesis test. So it's not a bad idea, but I'm not going to ask you to formally do it on a typical problem. You can't do it on all of them. It would just take too long. Try to claim that the standard deviation of pulse rates for men is equal to 10 beats per minute. Whew. Okay. Anything else to follow that up with? All right.